All right, hi guys. So we finished this lab and we went as far as we did, as you can see. Let me get to the top in the April conductivity lab. So the key idea here is that we did this lab because we wanted to illustrate these principles that are really shown the best when you're able to see them actually and hold on to them. So we were using the conductivity probe to put into solutions to see what actually happened. Because since ions are invisible and particles are invisible, we have to figure out ways to measure them that indicate to us what's actually in the solution. So conductivity in solutions, when does it happen? It's a property of the solute that you dissolved. All right? It's a property of the solute and its interaction with the solvent. All right, so we went through all of these today, and we talked about the tap water versus distilled water, sugar water versus salt water. All right? So now let's go down here. So we were working on these conclusion questions, and we had discussed all of the data, and then you answered the the simpler questions, but you still had to use technical details. Now we're going to delve deeper. And once again, the explanation states the main point and gives details, but these are technical details. This is not the stuff you knew when you walked in the door. This is what we've learned because we've done this lab. All right. So what is it in the solution that makes a solution have significant conductivity? And we saw that ionic solutions, if they dissolve, conduct electricity. All right, so there's something about ionic solutions that is unique. And the way that an ionic solution differs from a covalent solute is in that ions. So we assume it has to be the positive and negative ions. And this is the kind of reasoning that I want you to be doing. All right, you're not just copying off what I'm saying. I'm wanting you to think through this and see how isn't this exactly what we've been talking about now for quite some time, building little by little on these facts so you can reason that if it's ionic solutions that are conducting electricity, so it must be the things that it's made of, because ionic solutions dissociate into the ions. All right? 7 says, make a statement about the conductivity of dissolved ionic compounds and why that occurs. Well, in 6, we led right up to that. All right? The conductivity depends of an electric current depends on movement of positive and negative ions. We know all particles are in motion. All ions are in motion. All right? Of the positive and the negative ions. All right? It's the fact they're charged that matters. 8, when sugar dissolves in distilled water, there's little conductivity. Explain why that happens. Well, we're left thinking there must not be many ions. There must not be many ions, charged ions in sugar when it dissolves. There must not be charged ions in solution when sugar dissolves. Right? So if it's not ions, you're probably wondering, well, what on earth is going on in there? So, if we have a beaker of sugar water, all right, let me make it gigantic. All right, there's no ions, so we put sugar in, C12H22O11. All right, we put that in, and it stays just the same. This whole molecule, CH and O, all right, it's in there as the whole molecule. You notice nothing's charged. There's no positive or negative charges in this thing. It exists as a whole molecule in solution. So if it doesn't have any charged particles, then it can't conduct electricity. All right? So that explains why one of the properties of ionic solutions is that if they dissolve, they are good conductors in a water solution. Or if they don't dissolve, they don't conduct, because we couldn't even do the measurement right. But if they dissolve, ionic compounds will dissociate into ions and will conduct. And that's how they are different from covalent compounds. Now, we didn't do vinegar. I had too many samples. So how does HCl differ from vinegar? Well, if you had done this, HC2H3O2, this is the formula for vinegar, and there's the acid hydrogen. And this is the formula for HCl, and here's the acidic hydrogen. Well, the thing is, this hydrogen only rarely ionizes. That means become an ion. If I ionize you, you become an ion. It only rarely ionizes, where this one always ionizes. All right. So vinegar is called a weak acid, and because it doesn't ionize much, it doesn't act much like what we like an acid to act like, whereas HCl is a strong acid. True or false? All compounds that dissolve in water will conduct electricity. Yes. No. No. What's the fallacy there? All right. What's the fallacy there? All ionic compounds that dissolve in water will conduct electricity, but some covalent compounds dissolve in water and don't conduct electricity. Some covalent compounds, like sugar, dissolve in water. Some covalent compounds, like sugar, dissolve, but they do not conduct electricity, with the exception of acids like HCl. The solution will not conduct electricity. I'm too close to the bottom here. Let me do this. All right. But they do not conduct. The next one says ionic compounds produce positive and negative ions when they dissolve. Yes. True. Yes. The positive ions, remember, are called cations, and I drew my famous picture. And it's a cat with a positive charge to remind you that it's a cation that's positive, and negative ions are called anions. Occasionally you'll run across those words. All right. So what is an ion? An ion is simply a charged particle. Atoms are neutral, right? Atoms are neutral. Ions are charged particles. That's how they're different from atoms. Either plus or minus. All right, so we looked at these acid definitions that we talked about today, that an acidic molecule dissociates into H plus ions even though it's a covalent compound. So this was an exception to that rule. And bases, the typical water bases, dissociate into the hydroxide ion. So that's why we tested NaOH, and you could also do KOH or NH4OH, which is just ammonia dissolved in water. These are all typical aqueous bases. That means in water solution. Aqueous, agua, aqua. Yes, aqueous means water solutions. Typical bases in water. Yes, in water solutions. Okay, so we've covered so many important concepts in this. So this was review B, because I was using conductivity to pull together so many of these ideas. Now, let's go back and look what A was. All right, review A was when you went through and you were looking for ionic compounds that are metals bonded with a nonmetal, and then covalent compounds, which are nonmetals bonded to another nonmetal. You know that metals are all on the left side of the periodic table, and nonmetals are on the right, because we've learned that over and over. All right? Knowing where metals and nonmetals are on the periodic table helps you to think through this. Covalent are two elements from the same side of the periodic table, the right side. All right, so the big thing here is that you had to recognize whether a compound was ionic or covalent. That's what this part was about, because the naming is different. So if something has a metal in it, then we know it's ionic. So let's go look. Aluminum, carbon's not a metal, nitrogen's not a metal, hydrogen's not a metal, but sodium is, magnesium is, aluminum is. So we know if they have a metal in them, the other one will be a nonmetal. Lithium is, etc. Copper is a metal, so we know all of those that have a metal in them are ionic compounds. All right, so we know that those that have two nonmetals in them, carbon and oxygen, nonmetals, both on the right side, carbon and one. So dioxide is for the two oxygens. Monoxide is for the one oxygen. All right, ammonia, NH3, you just have to know because that's an ancient name for it that's never gone away. Water, similarly. All right. So then we were also looking at those transition metals that have more than one kind of charge. And it's because of the ability to do not only S and P, but D orbitals in their bonding. So we've seen that copper 2 sulfate in the name means it's Roman numeral 2, and all metals have a positive charge. All right, so we went through all of this. We looked at hydrates, where 5, the Greek prefix is penta, and we call the water a hydrate. All right? Now, all right? The polyatomic ions are covalently bonded nonmetal ions that have a charge. Those are on your periodic table. Now, this is old now. So we did this review to remind you, if you're having trouble with any of this, you really need to go back and finish assignments early on this month, because my expectation is you can do this now. All right. That molar mass you can calculate straight from the periodic table, because we practiced these earlier in the week. All right. That's my expectation. Now, what about today? Well, the last thing I wanted to talk to you about is this issue of bonding and how it gives compounds certain properties. So let's go right into here. The properties of ionic compounds versus the properties of covalent molecules. So remember, a covalent molecule is just a covalent compound. But they're called this word molecules that you've heard many times. These properties depend on their bonding. And whether it's a bonding of ions, like ionic, or atoms, like covalent. All right, so this is a huge difference, and this is the primary one. Covalent bonds are made of atoms. Ionic compounds are made of ions that are attracted to each other. Ionic bonds are strong, very strong. Covalent compounds, variable strength. All right, and we also learned about electronegativity difference. All right, so the electronegativity difference, if it's very large, makes for strong bonds. Oops. Large electronegativity difference between the metal and the nonmetal. If you don't know what electronegativity difference is, you need to go back and look at that assignment between a metal and a nonmetal. All right, so the larger the electronegativity difference, the stronger the bond. So we can see in this, covalent compounds can be very polar with a high electronegativity difference, all the way down to not polar at all, meaning no electronegativity difference. No difference. All right? And that would be like oxygen and oxygen. Two elements, I'll make those rather than atoms, I'll make them oxygen atoms, versus something like HOH, the hydrogen-oxygen bond, all right, is very polar. The oxygen-oxygen bond is very nonpolar. All right, and then there are many that are in between, but the strongest bonds are the very polar ones, because they're polar because the electronegativity difference is so great. All right, so properties, types of elements for ionic, metal and nonmetal, covalent, nonmetals only. Now, what about bonding? Well, ionic, attraction between anions and cations. So, negative ions and positive ions. All right, cations are positive. Whereas covalent is sharing a pair of electrons. So, I'm going to remind you again, ionic bonding. All right, so we will pick Na has a 1 valence electron. We'll show this with Lewis dots. And fluorine has 1, 2, 3, 4, 5, 6, 7. All right. And what happens is that sodium loses its electron to the environment, and now here it is up here. And what happens then is that fluorine has a vacancy right here, and it goes and lassos it and brings it right here. And so this guy gains an electron. All right? So this is why this loss of electron becomes a +1 ion, and fluorine, because it gains an electron, becomes a -1 ion, because it's the electrons that are the negative things. Correct? So examples of ionic bonds show electron transfer from one atom to another. And now they're no longer atoms. From one atom to another. No longer neutral. These are called ions. No longer neutral. These are ions. These are ions. All right? That's what ionic bonding is, a transfer of electrons generating ions. All right, so now this is the sodium ion, and this is the fluoride ion. They have opposite charges, and that's what the ionic bond is made of. Now the covalent is sharing of electrons. All right, so let's do one. We've done water quite a few times. So let's just do nitrogen. Remember, has 1, 2, 3, 4, 5 electrons, so it has 3 vacancies. Because it has 5, it wants to go for broke and get 8. All right, so that's the situation nitrogen finds itself in. The situation hydrogen finds itself in is it has 1 electron. We'll give it a little X. And it's missing 1 as well. It wants 2 because it in the inner energy level just has 2 electrons. So what happens? Well, they don't transfer electrons. The 2 atoms share their electrons. All right, so each gets 8. In the valence energy level. All right. So here we have nitrogen. Let's go over here with its, all right, 1, 2, 3, 4, 5. All right, and it has those vacancies. I'm going to just draw this one. And so hydrogen, all right, has 1, all right, and another hydrogen could bring 1, and another hydrogen could bring its 1, and so now hydrogen thinks it has 2, and this hydrogen thinks it has 2. This hydrogen thinks it has 2. And this nitrogen has 2, 4, 6, 8 electrons. So this is how the electrons are shared. And this little pea pod, all right, with the 2 electrons shows that there's an electron from 2 different, and these are shared between the 2 atoms. The atoms. And do you remember how we talked about polarity? Nitrogen's polarity is 3.0. Hydrogen's is 2.1, all right? That's a 0.9 difference. So what that means is that the when the bond forms. All right, and we'll have a bond here. So this would be the other way of writing it, where we'd show the bond with a line. Whoops. All right, we'll see how did I even get that there? There's a way to fix it. There it is. Okay. All right, that's the way it would look, right? It has those two up there already. All right, so nitrogen's the more electronegative, so everything's pointing towards it. And that means the electron pair is much closer to nitrogen than to hydrogen. And we said that when the electron pair moves away, poor little hydrogen now is partially positive because the electron pair, its own electron, is no longer close to it. All right, so now it has a nucleus and then an electron far away, and that's why it's slightly positive. Whereas nitrogen in all these bonds is slightly negative, slightly negative, slightly negative. So nitrogen is the covalent bond hog here, pulling the electrons closer to itself. All right, and that's partial charges. All right, so the unit of an ionic is the formula unit, like NaCl. Whatever adds up to 0, MgCl2, AlCl3. All right? The formula unit is this unit. Whatever's in the formula that adds, where the ions add to 0. All right? The formula unit here is the molecule. All right, it's the molecule, like CH4, like C12H22O11. All right, like H2O. All right, so the formula is just the molecule, and a lot of these we have to learn, or we have to name them by and try. So CO2, carbon dioxide, CO, carbon monoxide, etc. N2O5, there's many nitrogen-oxygen compounds. This is dinitrogen pentoxide. Okay. Now, what the formula represents in an ionic compound is the ratio. It represents the ratio of anions to cations. All right, so like an Mg plus 2 and Cl2, where each one's -1, all right, the relationship is always going to be 2 chloride ions with a -1 charge and 1 magnesium, and see how those are adding up to 0. So the formula shows the ratios of the ions of the different charges. But the formula in covalent compounds shows you the number of atoms of each kind. All right, so in ionic compounds, where we have a formula, we're always looking at the number of ions of each kind. All right, now what about states of matter? Well, most ionic compounds are solids. All right, they are like rocks. Rocks are ionic compounds. In fact, they're a conglomeration of many different compounds, many different ionic compounds. And so it takes a lot of energy to melt them, melt, or boil. So that's why you're not going to see ionic compounds as liquids. in our situation, since we really live from Celsius degrees, we probably live from 15 degrees Celsius to 37 degrees Celsius, which is body temperature, or a range of 60 degrees Fahrenheit to 100 degrees Fahrenheit. So these would be the typical ranges in which we live. All right, and in that, ionic compounds are solids. But many, many covalent compounds are gases. Isn't CO2 a gas? Isn't O2 a gas? Isn't carbon monoxide a gas? Isn't ammonia a gas? All right, so many, many covalent compounds are gases, which means they boil at a very low temperature. All right. Now, if they're liquids, that means they melt at a low temperature. All right. And if they're solids, it just means that it takes more heat to move the particles apart. I'm nearly done. All right, water solubility. Well, we know that ionic compounds are very soluble, except for the ones that aren't. And remember, we saw the solubility chart, and we saw that most of the compounds are soluble, and we saw that phosphates, sulfides, etc., are not very soluble. All right? Heavy metals are not very soluble. Mercury isn't. Lead isn't, etc. But we have the solubility chart to tell us which ones dissolve. All right? So it's high, and then we use the solubility chart. All right? And you're an expert at doing that. All right? Well, covalent compounds are often more soluble in oil. Smaller compounds, smaller molecules can dissolve in water. Like sugar. All right, like vinegar, for example. All right, melting and boiling temperatures we hit here because melting and boiling depend on the way the particles are arranged. The bonds in the case of ionic, are so attractive that it's hard to get a simple formula unit apart. So bonds between neighboring particles are so strong. They are actually ionic. So everything is ionic. It takes a tremendous amount of energy to break apart conglomerations of these little formula units of ions, because they stick to everything else. Opposites attract. Whereas that's not true of covalent. They're much looser. There's only weaker intermolecular forces, like we talked about. Holding neighbors together. So electrical conductivity, we found out ionic compounds are exceptionally good. not only when they're in solution, but when salt is molten. That is, molten means melted. So if you take salt to a high enough temperature that you can melt it in that liquid state, the ions will conduct. Yes, that's true. Whereas covalent compounds are poor conductors of electricity because ions, remember, don't form. All right, state when dissolved in water. These guys separate into ions, and that's called dissociation. Whereas these remain molecules, no dissociation. So what's the opposite of dissociation? Yes, atoms within the molecule stay associated. All right, now, do you see how we've reasoned through everything? Yeah. All right, we've reasoned through everything. No wonder my little descriptive things were missing. All right, now, this is going to be a hard test. I believe it will be because so many of you have really delayed. So remember, when I'm not there, that doesn't mean that you can slough off, does it? Because you know what I'm like. Yes, you know that I expect you to work. You know that I think you're very intelligent. And you know that I think that you really push your intelligence to achieve when you just try and work on these things. It just takes your effort. All right? So I have every faith in you. You can do well if you're willing to work at it. All right? So, I think that's it. The test will be Friday, and it won't be easy, so certainly come prepared. All right? You, of course, can use your periodic table, and that has the polyatomic ions, as well as the order of the elements. All right? And everything else that you need to know to realize what kind of ions each element forms. All right? I'm pushing for you. Talk to you later. Bye.